Refrigeration is everywhere in our modern world, and what I'm going to do in this video is describe the thermodynamics behind what drives refrigeration to occur, and also discuss the underlying principles that you need to know. And so to begin with, if you've ever been in a car with the AC unit, you know that somehow we get cold air blowing out of the car despite the ambient temperature of our room and the car being slightly hotter. And as you're going through a thermodynamics course, you're also learning things such as heat will never flow from a hot object to a cold object. And so it can seem a bit counterintuitive, but fundamentally what's going on is we are making use of an endothermic process. And that endothermic process that occurs is the evaporation of some kind of fluid. And in your car, it's called Freon typically, and there's different types of Freon, such as R12 and R134A. And what happens is your Freon will do a phase change from a vapor to a liquid and liquid to a vapor. And what we know intuitively about vapor is that the vapor has more energy, or a molecule will have more energy in the vapor phase than it does in the liquid phase. And so as we vaporize a molecule from a liquid phase into a vapor phase, it must grab thermal energy from its surroundings to do that. And as it grabs the thermal energy, it results in lowering the temperature of some unit. And so the way a car AC works is inside of your car, you'll have an evaporator. And in this evaporator, the liquid Freon comes in, and the liquid Freon vaporizes to become a vapor. And consequently, it's pulling heat out of the inside of your car. And that's what makes the inside of your car cool on those really hot days. And so to draw this out a bit more nicely, I have these two plots here. And the plot on the left, we see our evaporator. And so what's going on here is we are pulling heat, Q, out of our surroundings. And I will call this Q dot sub C. And this is to note that it is a rate that is occurring because your car is operating continuously. It's pulling a certain number of joules of heat out of your car per second. And what you'll find is in the engine bay of your car, you're going to have something referred to as a condenser. And in this condenser, that vapor Freon will then be turned back into a liquid Freon, but it does this at the cost of relinquishing the thermal energy that it grabbed from inside the car cabin. And the consequence of this is it's now going to reject heat to the surroundings, but it's outside of your car, which is where you want it. And so in your condenser, we have QH occurring. Now, if you have a home and you pay the electric bill, you know that running your AC doesn't come free. So the price of this is energy, and we need to supply energy to drive this process, this non-spontaneous process, and therefore we need a compressor in our loop. And in our compressor, we will have work done over time, W dot, entering our system, so kilowatt hours or megawatts of energy. And this is what's driving your refrigeration or your refrigerator or your AC unit. So refrigeration is everywhere, and it's very cool. Okay, so what we do next to begin to better understand what's going on in refrigeration is plot the saturation pressure, Psat, versus the specific enthalpy of our coolant. In this case, it could be Freon. So we'll say Psat of Freon, for instance. And this is not necessarily an accurate plot, but it gets the gist of the concept through. And so if we make a plot of how the specific enthalpy of Freon evolves as a function, or I'm sorry, the saturation pressure of Freon evolves as a function of its specific enthalpy, we'll get a plot that kind of looks like a upside down U to an extent. And what's happening is this inside here, the Freon exists as a liquid. And outside of the saturation pressure, Freon exists as a vapor. And so at these boundary points here, the Freon is in between, but generally you will want it to be entirely a vapor if you're passing it through a compressor, and if it's going through a pump, you're going to want it to be entirely a liquid. And so because it is a continuous loop, it really doesn't matter where you start in this process, but I'm going to call compressor point 1. And so at point 1, what we see occurring in our pressure versus specific enthalpy plot is the pressure is increasing. And that makes intuitive sense because the point of a compressor is to compress the fluid to raise the pressure. But we also see that the enthalpy, I'll call it delta H is also increasing. And so your compressor has taken the Freon vapor and raised its pressure. And what happens next in the car, for instance, is it's going to pass through a condenser. And in the condenser, we're going to be rejecting Q moles or joules of heat per second to our surroundings. So QH, and this occurs in your car because you've got cold air coming into the engine bay, and that phase is taking the thermal energy out from the Freon coolant. And as this is happening, the pressure is remaining relatively constant, so there's no change in delta P, but the enthalpy, the heat of the stream, is decreasing, and therefore we see our line now shifting to the left on this plot. Now at point 3, we're going to use an expansion valve, and the only purpose of this valve is to decrease the pressure, and we're going to assume it's an isenthalpic, meaning no change in enthalpy valve. So we're just dropping the pressure, so we drop the pressure, and the reason we're dropping this pressure is to help make things easier for when we enter our evaporator. And inside of our evaporator, what's happening is because we've decreased the pressure significantly, we now have this nice regime here in which we can take in QC, joules of heat per second, from the car interior. And because of that, your car interior gets cooler. And so this kind of illustrates the main process of what's going on. If we were to perform some kind of energy balance on our system, if we just treat the refrigerator as some kind of black box, what we'd find is that we're going to have QC joules of heat entering per time. We're going to be supplying work into our system, and we are going to be rejecting heat to our surroundings at a rate equivalent to QH dot. And another important thing is when you're generating these plots, so I'll call this table 1. Table 1 here, the control volume is the Freon. It is the stuff inside of the refrigeration loop itself. We're not looking at the car cabin over time. We're not looking at the exterior. We are only looking at how the Freon is evolving as a function of specific enthalpies. So that is an important note to make if you are going to go ahead and generate these plots or try to understand this stuff better. And so getting back to our energy balance on the Freon, what we will find is that you can quite simply say whatever's coming in must be equal to what's leaving because energy is conserved, and therefore we can say that QH is equivalent to QC plus whatever work you're performing on your Freon over time. And so in a car, this is the lost work due to the belt that's driving the compressor in the engine bay. And so these are the quantities you get. And so if you were actually buying a refrigeration unit in practice, how do you differentiate between the good, nice model and the bad model. And so the way you do that is people define something referred to as a coefficient of performance, COP. And COP intuitively tells you what you want, and you divide it by what you pay. And so in this case, what we want is to take in heat from our car's interior at a rate QC joules per second, but what we pay is the work required to run our compressor. And so we want to raise, or we want to have the highest COP we can, so a better fridge has a better, higher COP, and generally COP is approximately 4. And so what this tells us is that if we wanted to rewrite our energy balance right here in terms of QC and QH only, W is equal to 1/4 times QC, and therefore QH is equal to 1 plus 1/4 times QC. And in other words, what this tells us is that we need to, or we are going to be rejecting an additional about 20% heat to our surroundings. And so what this means is like if we wanted to remove 100 joules per second of heat, then it tells us that we're going to need to have a condenser that can handle approximately 120 joules per second of heat rejected. And typically the joules per second is equivalent to 120 watts of power. And so this wraps up the concepts behind refrigeration and coefficients of performance. Another key thing to make a note of, if you're in a thermodynamics course or you're still interested in this stuff, is the direction that we are going in our P versus delta H curve here in figure 1. Note how refrigeration is counterclockwise. And if you're interested in instead running this process in reverse, if you wanted to heat up a stream, then heating is clockwise. And so what that means is if we instead wanted to turn our refrigerator around and heat up or preheat some reactant feed, for instance, in a chemical process, we will simply change the directions that we operate our refrigerator in, and we can do that. So it's pretty cool stuff. I hope you guys find it useful. Let me know if you have any questions, and thanks for watching.